So before going into the subject, two important points. First, of course, I would like to thank the organizers for this very kind invitation in this nice workshop, nice summer school. So thank you sincerely. And second point of importance as well is that everything that I will present is collaboration with people from my lab. So Vassos Achilleos, Olivier Richoux, Yorgos Theokaris, L'Aume in Le Mans. And then as well, Antonin Coutan, that has now moved. So he was postdoc with us, now he has moved to Marseille in the LMA lab. And Liyang Zheng, that has moved, has got a position in Shenzhen, China. And so my subject today will be about networks of acoustic waveguides and to see what kind of effect of symmetry and topology can occur in this kind of setup. For the context, Sampikos has done a marvelous introduction on the control of waves. So it's about this type of how to control waves. So it's a way to control waves in this network of acoustic waveguide. So just to be clear on the objects that are at stake. So it is network of acoustic waveguides. So really waveguide like tube, pipes, ducts, very down-to-earth object like that, pipeline stuff. And it is just how to branch and to arrange assembly of this kind of tube to have a funny behavior for the wave propagation. So just one example that I will show at the end. Example of what is possible is this setup. So here it is a waveguide. It is a strip, a waveguide as Fabrice has shown this morning. So it is a network done by way of Kekulé. So Kekulé is like a graphene, but with alternating coupling. So here it is a COMSOL computation for the 2D wave equation. So it's really Helmholtz equation that is simulated here. And it is how to get immune to backscattering setup. So here it's at a frequency where there is an edge wave, as evoked this morning as well. There is an edge wave propagating on the bottom. And here, due to the chirality of this lattice modeling behind that, and due to the mirror symmetry, and so we call it chiral mirror symmetric network. So today I will try, because chiral, I've seen that it's very confusing. I will come to that after. I will try to say every time chiral bipartite. And so in this setup, we have invisibility. So the wave is transmitted whatever the defect that is respecting the mirror symmetry. We can cut any defect, and then we have the wave that is passing above this defect. So perfect transmission, and not only perfect transmission, even invisibility, because there is no phase as well. So T equal 1, the complex transmission coefficient is equal to 1. So it's not broadband. To be fair as well, it is for one particular frequency, but whatever the defect is going through. So that's one example, and that's example where we cut different type of mirror symmetric defects, and we see always this T equal 1. So one example of what we are doing with this network of tubes. So in this example, this invisibility is coming from two symmetries. So mirror symmetry, so it is right-left symmetry can be obtained in any system in general, but the other is the chiral symmetry bipartite. And this one comes really from the discrete lattice modeling that is behind this type of setup, and it is the gain. And so, in general, with this network of tubes, we'll go to lattice models, trying to use and to take advantage of symmetry and some topology argument to have different kind of properties, meaning that we will transform the wave equation to a discrete system of this type, so where H is a matrix, H like the Hamiltonian that you have seen this morning as well. X is the vector unknown that will be the pressure at each node, and E, the energy, that will be directly linked to the frequency. So why it's interesting? Because first, so I will repeat over and over, this morning. So you have seen this morning block bond that can go to topological index. So in this type of system, as this morning, looking, you can have Zach phase, winding number, a lot of index that is telling you that with this building block unit cell, after you can construct interesting physics. Then you have the symmetry of H that can be of different style, like the chiral one. I will go back after, and as well something else that can be latent symmetry. And something interesting as well for us is that there are many lattice models that are available and just waiting for us to try to emulate them with this acoustic network. So SSH that we will see, Kekulé, Kagome, graphene, etc., etc. And then all that, most of the time, is coming with edge modes, robustness, that is an important word in this type of activity, and some scattering property. So to be complementary to this morning, here I've just selected few parts to illustrate the simplest model of topological wave that is called the SSH to Su, Schrieffer, and Eger. And here it's copy-paste of this excellent book that is very simple, very efficient to explain really the many fundamental basic concepts on that. So SSH, it's looking like this, so it's a chain. So it's coming from a paper by these three people in the 70s. So if I remember well, it was about polyacetylene stuff. So it's really a super simple model. It is a 1D chain. So you see the sites that are white or gray here. And there is just, what is particular here is that you have two coupling. If you take, for instance, here, I am deciding that it is the unit cell. You have the intra-coupling that is V. And then between two molecules with two atoms, you have the extra coupling that is W. That's all. And then when you write the problem for this 1D chain, it's going to just a matrix vector Hamiltonian equation like this, where typically the Hamiltonian is really simple like this. So it is 3 diagonal, nothing on the diagonal, of +1 and of -1, V or W alternating. So it's really easy to play with this matrix and to have the property of the simplest model of topology. So to repeat once again some aspect of this morning, if we consider this chain, the unit cell is the AB, then we can go to a block Hamiltonian that is just taking care of the unit cell. The block Hamiltonian is looking like this. And then from this block Hamiltonian 2 by 2, we have a two-bond system. And we obtain this two-bond system, so meaning the dispersion relation energy as a function of K, the wave number, the block wave number. We have E of K in closed form expression that we can take a look. And that's where is coming this topological transition in this simplest model. So here, I show the two bond when I'm varying the two coupling coefficient V and W. On this side, here, on the left, V is more than W. In the middle, we have V equal W. V equal W is really the trivial chain, just a 1D chain monoatomic. So we have the gap closing. And then we go to the other case, V less than W. But when you reverse V and W, you have the same bond. So here between V1, W06, and vice versa, it is the same bond. But for the same bond, that's where is coming some index here. So here I have chosen to copy-paste the winding number presented in this book. So from this Hamiltonian, block Hamiltonian, you can go to some representation of what's going on when you go through the full Brillouin zone, so came between minus pi and pi. And so you represent it in a 2D space of dx dy due to the polymatrices. So, okay, anyway, we can forget everything. It's just that we can represent what's going on when we describe the full Brillouin zone. So when we have V more than W, so you see that you have first a point, then a circle, and I have put a cross, a red cross at the origin. So here it is, after we just have to count the winding number of this circle representing what's going on during the Brillouin zone. And so we see that we are not encircling the origin, meaning winding number equals 0. And then when V is less than W, always we have the circle encircling the origin, and it's going to a winding number equal 1. And so this defines a nice topological index, and in between is the V equal W, where we have the gap closing described this morning as well.
May I make a small comment?
Yes.
It's not a nice topological index. It doesn't exist in SSH. Because as you know, you can exchange V and W, and you choose the opposite conclusion. So in fact, the topology of the SSH chain doesn't exist. It exists only when there is an interface. Because you have a prescription, a gauge prescription to describe the unit cell. And in this case, you fix the winding. But an infinite SSH chain has no topology. Because you see that if you change the unit cell, is defined in the oblique direction, you can define the unit cell in the other direction. So you exchange V and W, and you exchange the winding. So strictly speaking, is not topological, but that's true that as far as you are an interface, you can play with and this is what Schrieffer-Henninger showed. There is two copolymers with an interface, and the conjunction of polyaromatic molecule are due to just.
Thank you. Okay, so I call it a nice topological index. Nevertheless. Yeah, because I am more thinking about, I'm taking the unit cell and then I'm choosing from the beginning. So I don't care about this gauge stuff, etc. Okay, the important message is you have really V to compare with W, and it will tell you if you have something happening. And the something happening, for instance, here is if you take this unit cell and then you stick them together, when you are here, you will have a localized edge mode, and one at each end. Then, okay, so that's example of why discrete modeling could be of interest. And now is coming the how to go to discrete problem. Many people are doing something that is called time-binding approximation. So as you have seen as well this morning. So if I am right, Fabrice, you can tell me. It is what the results you were showing in this paper from yours. No, I know. It's, not, it's a rhetoric question. I was just adding during the lunch. But so one from the team of Nice, where you have seen these two resonator coupled, etc. And then I recommend this paper, 2020, by Wei-Kong Ma, that was taking as well two resonators and taking care of respecting the chiral symmetry. A very interesting one here. Anyway, we are not doing like that. We are doing differently. So we take here a network of acoustic waveguide tubes. And then we will take care of the pressure at each nodes, junction. And then in each tube, we will make 1D wave approximation, meaning that we are at low enough frequency such that there is only one mode propagating in this waveguide. At the junction, no surprise, we will apply pressure, continuity, and velocity, the flux Kirchhoff law as well, as usual. And importantly, what we are doing here is that we will always take network with all the tubes, all the waveguide of the same length. So here, meaning that at the end, all this system will be summarized in a system with 7 degrees of freedom, the 7 pressure at the junction.
Vincent, one question. You need always to have valency 3 at the vertices, or you can do...
Whatever.
You can do whatever.
Yeah.
Because in microwaves we have a problem. We have disjunctions and we are locked with...
That's the charm of tube. Plumery and stuff like that. Yeah, it's... okay, so what we are doing here, I call it a graph way, in fact. So Sampicos, for instance, is a native expert on graph. And we are here just using graph approach on Neumann quantum graph, even simpler than the Dirichlet quantum graph, where we know that when the slenderness of all that is going to 0, so when we take thinner and thinner tube, we are converging to the exact solution of Helmholtz. But we will see that it works well even with a network looking like this. And so in the language of graph, it's even equilateral graph that is allowing us to go to discrete equation. So this is a nice book as well I recommend for introduction on that type of subject. So how it works practically. So here I'm taking an example of a waveguide along the axis X here, and just 2D, and just with alternating width that I call SB and SA. So it's SB, SA everywhere. How it works, so we start from the 2D continuous wave equation, so Helmholtz here, plus Neumann boundary condition at all the walls, rigid wall. Then the monomode approximation in each tube segment, we can go to 1D wave equation now, but at each change of cross-section, we have continuity of pressure and continuity of flux. So from 2D to 1D, but we are still continuous. And then, since all the segments have the same length, it's possible to go to a discrete system with just the known pressure at all the change of cross-section. And we go to this type of system. And you recognize it is SSH, exactly. Where you have the coupling parameter that are directly given by the ratio of cross-section, SA and SB. And as well, you have the energy, E, that is directly giving the frequency of the wave K at the beginning. So there is directly a mapping. And so the SSH equation is written there. So more into detail, how it is going discrete so simply. So if we are interested in this point here, we want the equation corresponding to this atom or this site. We just take the two neighbors at the right and at the left. So XBN is that guy, yes, and XBN minus 1 is that guy. And then we just apply 1D wave equation, transfer matrix, whatever you want to call it. And, okay, so we have a relation between the pressure at these 3 points, but we can eliminate the flux due to the flux conservation, and we obtain this discrete equation relating the point AN to BN minus 1 and BN. And it is SSH exactly like. Oops, sorry. So what it means is that now from this 2D waveguide, we have the 1D SSH model in the form really native SSH. And importantly, something that we like a lot is that on one side, we have an Hamiltonian that is just depending on the geometry. And that is very simply expressed by the geometry. And it is mapping to the SSH, really. And on the other side, we have the eigenvalue E that is directly giving the frequency. And so there is no complicated intertwining between the eigenvalue inside the operator or anything. And after, we can map directly. Every time we are able to do that, we can map directly to some interesting model of lattices. Then, something of interest is that this SSH has a chiral symmetry. So here, maybe I will take 2 or 3 minutes to insist on that, because this chiral word is very dangerous. So it's not the chiral of the end. It is just an algebraic property that is saying that gamma, some operator gamma such that the square is identity, is anti-commuting with our matrix H, our Hamiltonian. And this anti-commutation is coming with a very nice property that all the eigenvalue, eigenenergy, or as well eigenfrequency will inherit from that. You have this E to minus E symmetry due to this algebraic chiral symmetry. And so if you have 1 at E, you have another at minus E. To insist a little bit, in everything I will talk about today, this chiral symmetry will come from the bipartite status of the lattice. And the bipartite means that you take a lattice, so an assembly of tube, because after you have to imagine that all that is to model acoustic waveguide. It is where every junction, you can take 2 colors, A blue and B red, and A is only coupled to B and vice versa. And then you have automatically this chiral symmetry that is coming with the interesting property. So what is typically bipartite and thus chiral is any 1D chain, anything that you can put on a rectangular grid, then any, how it is called, polygon. Polygon with even number of edges. And then even if you have a triangle, it's not so annoying, because you can retransform it to something that is bipartite just by adding points in the middle. So we can attack like that any assembly of network of acoustic waveguide. The only problem will be forever to have the same length everywhere for any segment. And one very nice property of this bipartite and chiral symmetry is that if you count the number of modes, so here you take this geometry, for instance, it has 3 reds and 4 blue, automatically you will have a zero energy mode in this geometry. Whatever you do, whatever the tube are, you take thicker or thinner tube, in any case you will have E equals 0, meaning cos KL equals 0, meaning a lambda over 4 eigenmode automatically just counting the number of points at the junction. Okay, so we can continue with this 1D acoustic SSH. So here is just an example to see how it goes when comparing the lattice modeling and the 2D wave equation. So we take a closed boundary condition at both ends. So from the discrete, we obtain the energy, then we can compute the frequency. And so here it's a comparison of the 2D numerics with the points with the lattice approximation as a function of t, and t is just when we change the ratio So let's say that we keep SA constant, and we just change SB. And so we see, of course, at the lower frequency, it's where the graph approximation is working the best. Then when you increase, you see more and more the discrepancy. And interestingly, what you see as well is that you have this edge mode at lambda over 4 in each tube that is corresponding to 0 energy. So you have this edge mode at 0 energy all along, whatever you change here. And funnily, here in the middle is the gap closing, and the topological transition is appearing when you have SB equal SA. So the gap, the topological transition is just the trivial stride tube. So it's a funny mapping. About the robustness, so when we look at this edge mode at 0 energy, at lambda over 4, it is robust, and we have tested here how it is robust in the wave equation. So you see that you put a lot of disorder in the height, in the width of each waveguide, and you see that this edge mode is still there, is stuck to this edge here, and we can see that as well in the statistically making many realization of this computation, where you see that this edge mode at lambda over 4 resonance here is less sensitive to the disorder than everything else. The experiment, so since it's robust, it's true that the experiment is working quite well in general for this kind of system. So here you see a 2D waveguide with 3D, of course, but it is invariant along the height. So of course here it's closed after we put something to make it a waveguide. And it is alternating between SB and SA. So we see it from above. 10 unit cell, and here it is the measurement compared to the numerics. And so very, very close agreement. And as well, it's not so difficult to see the robustness to disorder of this edge mode that is stuck on one edge.
The numerics here, it is based on time-binding approximation? Or?
There is no time-binding approximation here. It's a graph approximation.
So no approximation?
Yes, graph approximation. 1D in each tube. The numerics, no, analytic, it is the graph system, because in this case, even we have the analytical expression of the edge mode. And the numerics, it is 2D wave equation. Just passing by, since it is very robust, it can be done in many different waves problems. So a lot of waves are governed by Helmholtz equation. So one of these waves is a water wave. When you take a flat bottom water wave, as we have seen yesterday, is following Helmholtz. And so we have done the experiment as well here, the same alternating channel for water waves. You see here measured by here some confocal sensor. So it's a collaboration with, so it was part of the thesis PhD of Adam Anglart, collaboration with Philippe Petitjean from PMMH and Agnès Morel from Langevin. And then here, once again, this object, this edge mode is very robust, and you see that between the 1D, the 2D numerics, and the experiment is very good. Just a remark, so here, due to this equilateral graph, so every segment is the same length, we have this direct mapping between the eigenenergy and the frequency. But it's not mandatory. In fact, we can equip each segment with anything we want, as long as that the phase in each segment is the same. So KL is the phase in one segment when there is nothing inside, but we can put a resonator as well, so that's what is shown here. And so here it is segment equipped with Helmholtz resonator, and it's possible to play all the same game, but instead of KL, the simple KL, we have a phase phi of K that is depending on the resonance, and it allows to go through wavelengths, because of course this zero energy, it's going to KL equal pi over 2, so quarter wavelengths resonance, but with that we can go to much smaller. And so here it is how is looking the edge wave playing this approach. Okay, so next it is possible to go to 2D, and even I will not show 3D, but it will be as well possible. You take just tubes equal length and you can do it. So the same approach, tube of same length everywhere, just one mode propagating, and then conservation of flux, so Kirchhoff law at each junction. And then you go to discrete, typical lattice equation. And for instance, here it's a realization of the 2D SSH. So 2D SSH, it is, so as the name is quite obviously indicating, it is in each direction, it is playing the game of alternating hopping. And so we were designing it with this kind of, so once again, all that we were putting something above to make it waveguide everywhere. And then it is a kind of CT with different streets, with different width at each part. And then here it was some measurement of the edge wave occurring for this 2D SSH problem. With this 2D SSH, it is as well possible to play with the corner. So here it's numerics. In this type of, so here it's a corner, there is nothing there and there. So there is a corner, and it's possible to find corner modes in this 2D situation. And this corner mode as well is coming with a robustness to disorder, where here you see that from this periodic case we go to disordered, and the corner mode is able to be stuck. And this robustness, by the way, is coming with a funny conservation. We had just to conserve some kind of flux on the strength of the coupling on the double cell structure, something like this. So it was something that was very, very linked to the chiral symmetry I was talking about. Okay. So now something that is particular to lattice modeling is that we can have funny symmetries that, like this one called latent symmetry. So I prefer hidden symmetry. So that's a work with Malte Röntgen, Christopher Morcionos, Maxime Piz, and Peter Schmelcher from Hamburg. And the idea of this latent symmetry for lattice modeling is the following. We have this kind of lattice model. You are looking for lambda, the energy. And then so meaning that you have a lattice setup, and you decide to separate the lattice in two subsets. So here I've called S and S bar. And then, as you can see, we can decide if we want to eliminate two equations to a known. We can eliminate the S bar problem. And then we put it back to the S problem. And then we have a new system that is just reduced on the S subset. So something that is very reminiscent of effective Hamiltonian here, but it is discrete. So now, okay, we can always do that. It can be very complicated, but if S is 2 points, it can be possible, a little bit more possible. Then, if we are able to produce a reduced Hamiltonian that is called HS tilde, in the form ABBA. So the work is to, in fact, since this reduced Hamiltonian is symmetric, we have always B of diagonal. We just need to be sure that we have the same diagonal term. If we are able to make that, then the reduced Hamiltonian is going to symmetric, because now the points on S will go, due to this form, ABBA, it will go with this eigenvector, and so you will go with parity symmetry.
What do you mean exactly by S is 2 points? You mean in the entire lattice you consider?
We will see after. We have 10 points and you choose 2. Or let's say the example is coming here. So here we were playing that with acoustic tube once again. So from tube we go to discrete lattice. And so if we take this waveguide, so it has 1, 2, 3, 4 points. Then we decide, let's make it symmetric for point 1, 3. Okay, so we start from wave equation, we go to discrete. Then from the discrete, we make this isospectral reduction to obtain the latent symmetry. And when we do that, we see that to have the latent symmetry on this 2 red point system only, we just need this relation on the width of this waveguide. Like this, a very, very simple expression. And then if we look just at these 2 points, the system is symmetric, even if, as you see, globally, it's not at all. And so after you can look at that numerically. So here it is a 2D Helmholtz solution. So we look at the modes of this cavity. And here it is the first 7 modes of this cavity. And by using this latent symmetry due to the lattice equation, you see that at point 1 and point 3, always, whatever the modes, you have the parity symmetry acting. So meaning that here it's normalized at 1 at point 1. And at point 3, forever, it will be +1 and -1. So meaning that this geometry is reacting as if symmetric when you try to inspect it from these 2 points.
So does it mean that you reveal hidden symmetry which cannot be seen on the complete system, or do you impose a specific
No.
symmetry?
Here it's coming with, let's say, it's coming with something, a constraint that is to choose the width like this. So you have 3 widths here, 1, 2, 3, and you have W1 equal W3 plus 2. That's all. If you have this geometry, like here, so this width is equal to that plus that, it's coming with this property of you are looking symmetric if you inspect at these 2 points.
Okay. It is in the same way you input 2 nodal points on a string and you select a subfamily of
Points.
eigenstates?
No, it's all the eigenstates here. No, it is from continuous, you go to discrete. In the discrete case, you have this latent symmetry where it looks symmetric when you look just at these points. What is interesting is that it is modular, this property. So here it is a 4-point system where we were able to make point 1 and point 3 latently symmetric. After, if we go to how many? 6 points, it was possible as well to find a good relation between the coupling to have 0.6 and 0.10 latent symmetric, and then we can glue them. And now you obtain a larger and much more complicated geometry where the 0.13 and 610, these 2 subsets, they are respecting the parity symmetry on these points. So here is the numerics for, once again, Helmholtz equation. So these points now going to waveguide. It is this is 1, 3. These 2 are 6, 6, 10. And then when you look at the eigenmode of this geometry, these 2 pairs are coming with parity symmetry. And then we can continue this modular construction. If we take this geometry and now we plug onto it now cavity 2D real, that is parity symmetric as well, mirror symmetric. Now you have the full setup that is coming with these 4 points, where it is parity symmetry at these 4 points, and you keep it in the 2D cavity that anyway is by itself mirror symmetric. So you can, like that, modularly construct whatever you want. Now, this latent symmetry as well can be used back to the SSH 1D chain. So that work is as well, in addition, collaboration with Xin Chen and Wen Longao from Ningbo, where if we reconsider the SSH, so SSH is like that. It is a series of pairs, of blue-red pairs with extracoupling T. And then this pair by itself, isolated, it is mirror symmetric, because it is with just the inner coupling that we have seen. But now we can consider that we put a more complicated network inside, and we can make this network with latent symmetry at the 2 points, red and blue. And so, for instance, inside the molecule, let's say, we can put this type of graph or lattice, or this type of lattice. And then if we make this lattice latent symmetric at the blue and red point, then we can try to reapply directly SSH. So that's what we have done here. So, when we do the isospectral reduction, due to all the dynamics inside, we are making to appear a self-coupling A, that is the same on both sides, blue and red, and we are making to appear a new coupling S between at the interior of the molecule. And then we can play with that periodic system to recopy what SSH modeling is doing. So first, this A, of course, we can put it on the other side. We have a new energy, and then here you have the Hamiltonian block Hamiltonian of SSH with a renormalized energy. And now it's going direct to, let's go to apply SSH sequence. First, we know that the topological transition of SSH is when energy equals 0. So we just need this renormalized energy epsilon to be 0. So here it is what is done. So we take 8 sites inside the molecule of SSH. So we just solve the renormalized energy equals 0. It gives candidates of energy to go to topological transition. And next, you can have the new intracoupling S, depending on energy now, that you can plug, coming with resonance internal. And then to have the topological phase, you just need, as before, to have the extracoupling more than the intracoupling. And then from like that, with this type of SSH equipped, you have many topological transitions appearing due to the internal dynamics of the molecule. So here it's an example afterwards of 12 cells. So in fact, since in each cell there are 8 sites now, it's total 96, and it is edge wave appearing in this type of chain with latent symmetry. Just a funny remark or funny property is that when we are using this latent symmetry, we can reverse. So if the lattice here is looking mirror symmetric blue-red, we can reverse, and red-blue is mirror symmetric as well. And so forever, we can make like that a chain. That is, we have dubbed that orientational disorder. And this, when you will inspect the dynamics just at the blue and red points, will appear as perfectly periodic. Just a funny, maybe trivial, but funny remark. Now, okay, just to end the last minutes, I'm back to the initial example I was showing with the invisibility with respect to defects. So this invisibility is coming with chiral and mirror symmetry. So we take a lattice system. We ask it to be chiral bipartite symmetric, like so this anti-commutation. Mirror symmetric, okay, and then mirror symmetry and chiral are going together. So meaning that we are talking about this type of lattices. So 1D lattice, for instance, with the axe of mirror symmetry here, or this hexagonal case here, or this square. All these type of lattices have this chiral mirror symmetry. And then next, we have to construct a strip of this lattice. We have to be able to be in monomode. So we have to find a frequency range when there is only one right and one left going mode inside the strip. So this full blue is a waveguide now of the lattice. And then if we put some defect that is mirror symmetric, it will come to be invisible at 0 energy. So very briefly how it works. The mirror symmetry, as usual, as often, let's say, allow us to separate the scattering problem into sub-problems, one symmetric problem, one anti-symmetric problem, and to play with two different reflection coefficients, reflection symmetric, reflection anti-symmetric, okay, on one side. And then the chiral symmetry is giving a nice property on the reflection and transmission coefficient. So meaning that if you are at 0 energy, this chiral symmetry is imposing that T is purely real and R is purely real as well. And then when you look at what's going on when you put a defect, you obtain the symmetric reflection coefficient at 0 energy is 1, the anti-symmetric is -1, a little bit as if we were doing the trivial case. So it is rigid wall coming with 1 and soft wall coming with -1. And then we obtain transmission equal 1 at 0 energy, meaning once again, this 0 energy is coming back and back because chiral symmetry is providing that, and then after it corresponds to quarter wavelengths in the tube. So first, how it works with the lattice model, just the lattice model. So here it is 3 types of mirror symmetric defect. So you see, and then here it is the absolute value of transmission and the phase of the transmission, and you see that indeed you have T that is going to 1 at this 0 energy. The point is that it is the broadbandness of the phenomenon is very depending on how is the defect, because to go through this crazy wall, it is the yellow curve where you see that it's really coming from some kind of resonance where it is a very sharp phase transition. But this type of defect that are more reasonable, they are, so for the blue, more particularly, that is that one, you have a very broadband perfect transmission with just a small drift of the phase. So meaning that if you are sending a wave packet, you should see just this time lag due to the phase drift a little bit. Still with the lattice model, so we can put as well disorder, not cutting the defect, but just putting a disorder in the coupling between each site, as long as they respect mirror symmetry. So that's what we have done, putting huge disorder on all the coupling here, but mirror symmetric. And that's the image of the transmission as a function of energy. And you see that it was really a very, very strong disorder here. And you see that, interestingly, everything is pinching, and you have always perfect transmission at this 0 energy. For tubes, now let's go to numerics for acoustics. It works well. So it is more or less the same as we were seeing before, with the same behavior of invisibility, where one stuff is happening, so we get the perfect transmission, but we see that the zero energy is shifted a little bit to another, but we still have the invisibility. And voila. Perfect. No. No, so conclusion. So it was the invisibility at zero energy for this type of waveguide / ribbon of lattices. Yes, nice playground for symmetry, yes, with latent symmetry. That is even something that we have tried to make it continuous. It's very difficult. This latent symmetry looks for us, for the moment, very particular to lattice. So what else? Yes, some what to do, broadbandness of all this effect, because zero energy is playing an interesting role. And after, I was not talking about that, but long-range coupling as well is possible. You put some tube that is going to the next neighbor, and you can play at will like that. Thank you.